And we give you our speaker, Joe Lucas, presenting Sandboxing Agents Workflows with WASM. Thank you, sir.
Thank you. Yeah, thanks, everybody. I'm Joe Lucas. You know what you're here for. I first became aware of the power of WebAssembly during JupyterCon 2 years ago, so I'm no expert. I was there to tell data scientists how easy it was to mess with their research, like modifying the integrity of their results or stealing secrets. But I learned a bunch of other stuff there as well. So I saw its demo of Jupyter Lite and was... Hello. We'll see. Just keep... No, that doesn't sound as good. This sounds better. I'm just going to keep eating it. Okay. Yeah, I'm no expert, right? I was messing with Jupyter, trying to hack it. I learned about Jupyter Lite, which is a Jupyter distro that runs in the browser, and I thought that was pretty impressive. So I tinkered with my own Jupyter Lite deployment, but really didn't take the lesson much further than that. Fast forward 2 years, and I'll show you this in the talk. I'm staring at newfangled AI libraries that call exec to generate simple plots, and I had this light bulb moment that I'm going to present. I had another light bulb moment that I want to take some time to talk about, which is that hackers should get out of hacker conferences. JupyterCon is a developer conference. For those who aren't familiar, Jupyter is a software ecosystem for interactive, usually Python development, popular in the scientific community. And so the attendees are core developers, plugin developers, and users. My talk wasn't anything that would be terribly earth-shattering to security researchers, but I got a lot of traction in that audience. Apparently, it was the first and only security-related talk that's ever been at JupyterCon. I saw people pull out their phones to take pictures when I pulled up Sliver. Many told me they hadn't considered the security context of their work before and were amazed by simple things like dumping the history out of databases and revealing secrets stored as environment variables. So for the most part, for our target audience, for people who will really move the needle on cybersecurity, they're not here, right? They're not at ShmooCon. They're at PyCon or CPPCon or whatever, and many don't have access to corporate security teams. They might be lucky to have folks in IT thinking about security. So try submitting to those CFPs. You might influence someone to whom your material is actually terribly new and relevant, and you might learn something. So with that, we'll start by talking about agentic workflows, then move into sandboxing, and finally, how WebAssembly can help. So what is an agentic workflow? Well, until recently, folks have had decent success using AI to generate code. Hey, ChatGPT, create a Flask app. But most of 2024 was spent copying that output, running it, maybe tweaking it, and going back to the LLM with an updated request. Why not just have the AI application run the code, iterate on any errors, and only return the output that you really want? That's the agency in Agentic. Operate some tool, like a terminal or a Python interpreter, and use or return the result. Because it can be a terrible idea. At least if done naively by executing the LLM-generated code in the context of the calling application. And unfortunately, that's currently the state of many libraries that might help you implement this sort of agentic flow today. Here's another more depressing light bulb moment I've had recently. I've always extolled the security value of open source. Anyone can audit it. And that's still true, but it's only part of the story. For solo and small developer teams, there often isn't anyone focused on, or with the necessary experience to focus on, security. Worse, there's sometimes a cultural aversion to security contributions for all the same old reasons that we've heard before: lower priority than features, degraded user experience, and there's often very little incentive for them to accept a PR. I think the canonical open source answer is just fork it, but security folks don't want to get in the business of maintaining those open source libraries. So does open source software still have a better security story than closed source? Certainly. But the fact that the code is public does not inherently increase our ability to secure it. There's still this kind of ugly human layer that we have to navigate. Here's a code snippet from a library that tries to do this simplistic, just exec it, agentic flow safely by using regular expressions to catch dangerous code. Dangerous code. Suffice it to say, there are plenty of dangerous Python snippets that would evade this regex. Building on my previous comment about open source security, this regex was actually added to the library by the maintainers based on fingerprints of a POC submitted by some of my colleagues. I'll just leave it at this wasn't the remediation they were going for, still a work in progress. Here's another snippet that, given something that's supposedly Plotly code based on the variable name, just carelessly shoves it into exec to get the resulting image. I understand what they're trying to do here. There are many applications where you'd want to return an image to a user, not just a blob of code that they need to run themselves. But the whole question of, is it even Plotly? And more specifically, is it the Plotly that I want, is the crux of this whole problem. How do you know that the code returned from the LLM will do exactly what you want with no security relevant side effects? It's hard, and the broader range of inputs and outputs you hope for an agent or tool to handle, the harder it is to provide any security guarantees. These aren't unpopular libraries. This is the flow that you'd be using with one of the two libraries that I showed you. In step one, we want a user to be able to interact natively with natural language, just the way we talk. That's going to come back to the application, and it will probably get rephrased by an LLM into a task, like generate Python. Another LLM or the same LLM with some prompt engineering is going to generate that code in step 3, ship it back. It's going to get executed on the application server in step 4, and the user will get their image. Here's how they show it in their tutorial. This looks small. So they have this object that they call a smart data frame, which is just a wrapper around the classic pandas data frame. For those of you not familiar with pandas, it's just a cornerstone of data science and has been for many years. And a data frame is basically a table. So their example here creates 10 countries, gives them GDPs and happiness indexes. Then they wrap this classic data frame in their smart data frame construct and chat with it, chat with your data. So here they say return the top 5 countries by GDP, and what the functionality that you're supposed to be gaining here is that you don't actually have to write the programmatic query. You're writing in natural language and getting those results. So you can think of it here as like a rough replacement for writing SQL. And it can show you the code that it generated, and it can plot the chart as promised. These simplistic workflows fail to adequately account for failure modes in the LLM-generated content. And these failure modes can arrive all too easily, either by mistake, or from a malicious user, or bad information retrieval, or a bad model. And by bad model, I don't necessarily just mean some sort of malicious poisoning, some boogeyman. Some of these things are just bad, like ineffective, incompetent, the kind of thing you wouldn't trust to let a stranger use to run code on your system. And that badness isn't always immediately obvious. There's still a lot of work going into accurately measuring and benchmarking model capability. And there's a classic data science principle called concept drift, used to explain the phenomenon of variables shifting in unforeseen ways, degrading performance over time. Many data scientists have shipped models and systems that they're proud of, only to have them yanked from prod months later. If you remember nothing else, remember to treat LLM-generated code as untrusted, particularly when users get some control over the generation. That's the part the devs don't like to hear. AI was supposed to save work and be this magic component, but it turns out that there needs to be plenty of scaffold engineering to make these systems effective, reliable, and secure. And now the AI bit of this talk is over. It was really just clickbait. Thanks for coming. The techniques we're going to discuss are just conventional code sandboxing techniques. But that's kind of consistent with my experience with most of AI security. Very little is new, but devs forgot these AppSec lessons already or somehow think that they don't apply. We're going to carry the Plotly example through the rest of the talk. You don't need to be familiar with Plotly. Just think Python in, SVG out. So in this case, we want to create data visualizations for our users. We've done a bunch of prompt engineering to give us some code. And this is the code example we're going to work with. What do we do now? Well, we're going to sandbox it, right? Here are your options. If you want to do a good job of isolating untrusted code execution, use a hypervisor, Firecracker VMs, and the like. This also includes serverless options like AWS Lambda that are built on Firecracker. Either way, you're trusting hypervisor isolation. You may take a hit in latency and cost, but it's about the best you can do besides bare metal and thermite. No one got fired for using a hypervisor. Don't use containers. They share the host kernel, and containers aren't a security boundary was hazed into me. But to be fair and complete, I will admit that there have been advances in container isolation and security. But what about browsers? That's what I'm here to propose today. Browser escapes do happen, but they're expensive. Unlike containers, there's at least the premise of a security contract isolating the browser from the host operating system. Even with that aside, moving to a client-side execution model provides great, dare I say perfect, isolation guarantees between the executing user, your server, and other users. And again, for the sake of completeness, I'll admit that this is largely an exercise in risk transference. I don't know about your users, but I know that all of my users update their browsers regularly, and so we can trust this. Okay, so given a set of Python functionality, how do we get it into our web page? Luckily, this templating can be done with minimal changes to our prompting strategy and requires only static templating. I say luckily because for the most part, prompt engineering is still a brittle mixture of guessing and voodoo. Without significant feature or scope change, your templates should survive evolutions in other application logic or model versions, as long as the prompt engineers preserve the expected Pythonic output. We're going to use Pyodide to do this. WebAssembly is a binary instruction format for stack-based virtual machines, and it's usually used as a compilation target for other languages. It started out for C and C++, but supports Rust and Go and others now. Pyodide does not equal WebAssembly. It's just the easiest way to get CPython-like functionality into your browser with WebAssembly. And here's what it does for you. It gives you the standard runtime requiring minimal code changes or special prompt foo, because LLMs are actually pretty good at generating CPython and might not be good at generating really weird WebAssembly instructions. It was built for the scientific Python community, so it has a lot of their libraries baked into it. But it gives you the tools you need to bring your own dependencies, either directly from PyPI or as wheels, and handles a bunch of other JavaScript and browser integrations, so that you can just worry about running your code. It generally abstracts away the difficulty of running Python in a browser context. Using Pyodide in the browser also gives us some configurable security controls. Browser context isolation is our first line of defense. We can configure the browser context with strict permissions, disabling JavaScript outside of WebAssembly, preventing CSP bypass, and restricting access to browser APIs. For network controls, we can implement request interception to prevent any unauthorized network access while still allow listing specific domains. Resource limitations, like memory limits and timeouts, can prevent resource exhaustion attacks. And just because we're executing client-side doesn't mean we should ignore the conventional input-output validation issues, particularly for LLM-generated content. Those filters can also give you a nice hook to kick off retries. And finally, error handling and monitoring give us visibility into what's happening in our sandbox. This is obviously useful for security, but also provides some good data back to the dev teams. The beauty of this approach is that many of these controls come for free with a browser sandbox model. We just need to configure them appropriately. It's also worth noting that Pyodide is the easy button for Python WebAssembly, but that means it ships with a lot. If you're really paranoid, you can ship a much more restrictive runtime. So here are some code snippets. At the end, I provide a link to a repo, but this is kind of the gist of what you need to understand. At first, you're going to init Pyodide here, and this is kind of where you're going to install your dependencies. Next, you're going to template your code. So if your prompting strategy didn't give you the necessary import statements, you might stick those in. You might need to do some string manipulation, and then you're going to return whatever object you finally want to return. And so now when you define your route, you can accept a request, grab the code out of the request body, and send that code to be run in Pyodide, and then return your SVG. So here's another example. To understand this in this blue box, I have some metrics. So here it took about 8 seconds for Pyodide to init. This text box is mocking our LLM because I like mocking LLMs and I didn't trust them with my live demo. And then we'll see the output below, right? So when you click execute, this is the WebAssembly running and generating your plot. If your LLM gave you something different, it would execute and run again. And you can see that the execution time is actually like really, really good. It's this init time where it's initializing that you take most of the hit. And if you try and execute before it's initialized, you are going to hit an error. Let's drop into developer mode. So what do we really have in here? In the HTML, we have the script. This is basically what I showed you earlier. And when we look at what was sent, you can see you're getting wheels over the wire, and then you have your WebAssembly. And this is what that looks like. This is the stack machine. There is a decompiler for the brave among you. I have not found that necessary, but this is what you're dealing with. There are a couple of benefits to this approach. One, we, the application owners, are isolated from bad users because we aren't execing their code on our servers. Two, we're protecting users from each other. Doing multi-tenancy well and cheaply and quickly is hard. Three, we use the user's compute. That can be a nice win for resource forecasting and allocation. With some clever design, we can use the user's data on their device. They don't have to ship it to us. There's a great privacy story there that I think people aren't using enough, and it's one of the primary use cases of Jupyter Lite, which I mentioned earlier. But nothing is free. There are some downsides. First, there are some ways that this is slower, as you saw during the demo. But a colleague also pointed out that in this context, it might not matter as much because the latency of dispatching the query and having the LLM compute the result may cover for that Pyodide loading requirement. One of the key elements of agentic workflows is that information may be routed between agents and tools server side. Think loops and branching logic. So what if you don't want the code execution returned directly back to the user, like we've been doing with this SVG? You might, for instance, want the plotly graph added to a prompt and sent to a vision or multimodal language model to analyze trends for the user. Headless browsers can provide a useful avenue here. While we don't have to budget for the code exec compute, we may lose the functionality associated with knowing the execution software and hardware stack. So right now it's hard to run like CUDA in WebAssembly, although there was a cool post about that this week. And then there's some cons about data management. If the data doesn't exist client-side, the LLM-generated code will need to include it. So think massive arrays instead of like a file read, which provides more opportunities for hallucinations and errors. So notice that this code had the arrays defined in the code. Here are a couple more things to think about. There's always a trade-off between development speed, user experience, and security. This is no different, and you'll have to win some arguments to sway adoption. It feels very much that we're still in the stage of make it work, we'll worry about security later. And so the majority of dev cycles are being consumed by just getting the required functionality working. Complex dependencies are going to degrade your performance, mainly in terms of latency and difficulty installing, and have anecdotally prevented adoption in some contexts. I've seen most WASM usage for numerical Python stuff, so that might be a good starting point. I got my stop flag. I'm behind schedule. This isn't PyScript. There's lots of WASM stuff going on in AI. Claude and ChatGPT Canvas use it. And a closing note on agents. Agent means a lot of different things. You're going to see it abused a lot this year, including in the title of this talk. So don't let the sales speak fool you. What I showed you today would be like a 0-star agent. For 1 star, we'd move to using the LLM output to switch between 2 static code paths. For 2 stars, there might be an LLM that determines whether to plot server-side or client-side based on some requirement like access to compute. And to move to 3 stars, refer back to my server-side example with a headless browser. Maybe the agent needs to graph the data, dispatch that graph to another model to analyze a trend, and based on that trend, trip your thermostat. Because, of course, we need agentic AI-enabled thermostats. Thank you. No questions? Great.
How's the bandwidth requirements of having to send over a whole Python, a whole C Python runtime manually? Does that impact client-side bandwidth?
I haven't done a ton of analysis about that. I think the biggest hit you're going to get is in the wheels. So as long as you're keeping a pretty trim dependency stack, I think you'll be okay in first world countries. The question was, have I looked into running WASM on the server as a lightweight hypervisor? No, but it is well documented on the WebAssembly site. Cool. See you, everybody.